Hello friends, I made one more circuit today. This is a current source, 0 to 20 milliampere current source that is useful for testing control systems when the field instruments are not available. This will simulate a 0 to 20 or 4 to 20 milliampere current that is typically output from the instrument. Now this simple circuit doesn't cost too much and it has got a nice display. It's all very cheap. It uses two op-amps. I'll show you how this works. Now I put that multimeter in that 200 milliampere range, and you can see this beside. Okay, now this is showing 0 milliampere in open circuit. Now connected is showing 3.4 milliampere. You can go right up to 0 milliampere, turn downwards. See this potentiometer, I'm using it to vary the current output, and you can see this. Now it is showing some 8 milliamperes, 8.57. This is showing. Now which of these two meters is more accurate? It can be a matter of a debate. We'll do that another day. Now, be that as it may, but this is useful enough to reach almost 20 milliamperes. See, is going to 19.9. Now that is limited by various things, because this potentiometer and all the trim pots and the resistors and even this display and even perhaps a multimeter are not really known for their precision. Okay, now next I will explain how this is working. Okay, now let us go to the matter of how this circuit works. As I told you, it needs two op-amps. The first op-amp is a transconductance amplifier. It takes a voltage signal and makes it a current output, for which we take an op-amp. This is the inverting and this is the non-inverting input. On the input side, we have a little arrangement to create that 0 to 10 volts. It is this 0 to 10 volts that is being converted to your 4 to 20 milliamperes. Alright, and for that purpose I take, this is 14K fixed, and this is a potentiometer, a 10 turn potentiometer, that is 10K. And here we apply 24 volt, and this is ground. Okay, so as we turn this potentiometer here, the voltage at this point, when this is 10K, the voltage will rise up to 10 volts, and when this is 0 volts, then it will go down to 0 volts. Now that we take it at the non-inverting input of the op-amp. On the inverting side, we connect a 500 ohm resistor to ground. Alright, and we use the feedback path to measure the output current. Alright, this is the multimeter. Okay, now it's like this. The op-amp is also powered by 24 volt, and this is ground, and this is VCC is 24 volt. Alright, then this resistor is 500 ohm. Let's say we are applying a certain voltage like 4 volts here. The op-amp will take care of that output, so that the current flowing into this resistor will create a voltage drop of exactly 4 volts, right? So that will be about 8 milliampere. That means 8 milliampere into 500 ohm will be the same 4 volts. Now at a maximum, when this potentiometer rises high to 10 volts, means 20 milliamperes will have to flow into the this 500 ohm resistor so that the inverting and non-inverting inputs are at the same potentiometer, same potential. Okay. Now we proceed on the second op-amp and how it works. Okay. Now we have this display. This display actually is a voltmeter. For displaying the 20 milliampere, we need to convert it to 20 volts. Then only this will display a figure of 20. Alright. But no problem, because since our op-amps are now working at 24 volt, that isn't much of a problem. Alright. So we take the second op-amp and make it a non-inverting amplifier with both the ground resistance, that is it is also 2K, and no, this is the inverting input. Okay. Okay, and it is this voltage we are, let us say, and that is the same voltage we apply here. We connect this VR point here. Alright, and these two are equal resistances. So as you know that the gain of this op-amp is 1 plus RF by RG, which are equal to 2. Okay, and this is what we are giving to this instrument as the measurement. This multimeter is also powered by 24 volt, and it's a 3-wire thing. Red and black wires are used for the 24 volt ground, and the yellow wire is the measuring wire. That is what is connected here. Let us show it at V. Okay, so that is it, friends. Try making this a very useful circuit for people in automation and all kinds of testing. You don't need a calibrator. The problem with a calibrator, I have seen, it uses a 9-volt battery, and that runs out very fast. So this is a very cheap and very effective substitute. And this can be made into this kind of circuit can be made into a more accurate, more precision version using better quality of resistors. And for example, this 500 ohm resistor is actually, to get some precision, I have used 1.2 K carbon film resistor in parallel with another 1K trim pot. Now that was critically adjusted. The parallel arrangement was adjusted to get that 500 ohm. So also this 14K resistor is a combination of 10K and 5K in series. Okay, and this 10K is a ordinary 10 turn, not very expensive. So as you can see, this works very well. One final look at the thing. It works very well, and I recommend everybody should make it. See. See, it can use. There we go. This is only a small 0.1 milliampere error. Now, as I said, now it is arguable now which is defective, that remains to be seen. Thank you and best of luck, guys. Have a nice day.